Hello everyone, welcome to this video. My name is Amir Sinahari. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to do wildfire detection using Earth observation satellite data in the Google Earth Engine platform. Let's get started. As you can see, I'm in the JavaScript environment in the Google Earth Engine platform. In the first step, we need to find the region of interest. As I'm gonna to do wildfire detection, it is important to know about the date and the location in which the wildfire already occurred. For example, I know that in October 2017, in the North California, there is a region that was affected by the wildfire, and also you can find the wildfire events in all around the world through the net by a simple search. So first of all, I need to find the exact location in the California in which in 2017 in the October that fire occurred. So to do this, I need to select this area as the region of interest. First, I'm gonna select this the state, the California state as the region of interest using the FAO administrative layer. Just through the search places and dataset, type FAO administrative unit layer. The first layer is available, imported into the code as a table. So then I need to select the region of interest. The region of interest is California. I'm selecting by a marker. I mark this region, and then I can filter the tables based on the marked region. Make a new variable for as a region of interest equals from input table. I want to filter based on the boundary of the location of the mark point or the geometry. Through the map.center object, you can have a focus on the study area, and using map.add layer, you can visualize it. After a few moments, you can see that the region of interest is selected. In order to increase the speed of processing in the Google Earth Engine, you can do the simplification process on the shapefile you are working. It's very easy to use technique, and it's very simple, and also same time is necessary to increase the speed of processing, as I mentioned earlier. So to do simplification on this shapefile, use the map and make a new function. The input to the function is a feature, and then in the body, function returning the same feature that is implemented by simplification. Inside the parentheses, you need to import the degree of simplification. That could be any value, and also greater values, higher simplification, and the lower values, lower simplification. For example, I set 10,000. Run the code again. Same time, you can see a simpler version of the region of interest with the lower number of vertices. That could be very, very beneficial to increase the speed of processing in the Earth Engine. That was the first step. Then I need to find the exact location of the wildfire in this region. Just I have a date and also, but I don't know the exact location. In this situation, coarse spatial resolution with high temporal frequency helping me to find the region that was under fire. So make a new variable, another variable as VIIRS. As you know, the VIIRS is one of the NASA Earth observation missions that is alongside the MODIS with the same characteristic, is very, very useful to monitor Earth surfaces, and it started from the 2013 and this is one of the best complementary satellite data alongside the modest data we are using. So this is the VIIRS. The spatial resolution is 501 kilometer, 500 meter, and 1 kilometer. Then to call VIIRS surface reflectance data, again go to the search places and dataset and type VIIRS surface reflectance. As you can see, the surface reflectance data with 500 meter spatial resolution is available. I'm going to use surface reflectance data because it is already corrected radiometrically and atmospherically. Import it into the code as an image collection. Then assign the image collection to the VIIRS variable. So next, we need to set the filter date. The filter date is very, very important. I know that the fire occurred in 2017, month October, and day 8 or 9. So through the dot filter date, I will be able to set to limit my data to the period of time that actually the woods and the forest were under burning. So the start date, the year could be 2017, and the month definitely October, and the day and the starting date could be the day number 8. So, and also the end date, we don't go too far from the starting date because, as you know, the wildfire is a dynamic process and also is a dynamic actually phenomena that is that could be vary from one time to another time spatially and also the temporarily as I mentioned. So that's why I'm selecting 2 days after starting days. 2017 again, month October, but the day number 10. So if you go to the data description in the bands, you will see the descriptions about the bands we have in this satellite data. As you can see, from January of 2012, I said 2013, that was wrong, sorry. But it is available since the January of 2012 until now, and also near real time is available. As you can see in the bands description, the bands with 1000 meter and 500 meter spatial resolution is available, and you can see and differentiate them easily. So if you want to have more spatial detail, you can use the 500 meter bands that is available in the near infrared region and also the red portion of electromagnetic spectrum. And there is no scale factor here. It is already implemented on the data, and just what we need to do, the only thing we need to do is select the target band. In the first step, as I'm gonna select the region of the wildfire or defining the exact location, just I want to make a false color composite. For example, I can use the band in the red and near infrared region, these two bands with 500 meter spatial resolution, for making a false color image to differentiate, to actually define the exact location of the wildfire. I number 1 and I number 2 are the names of the target bands, I1 and I2. So to do this, .select helping us to find the target bands. The target bands, the first one is I1 and the second one is I2. So there it is. When you print the result, print the VIIRS, in the right side under console, you will see that two images available. One of them for day number 8 and another one is for day number 9. So through the map.add layer, I can visualize these two images. The input for visualization is VIIRS data, and then I need to make a stack layer through the dot to bands and then clip it based on the border of California states. So next, leave the visualization parameters empty. In the layer setting, write the VIIRS Wildfire data and use the false at the end. Save your code and run it again. The code is under running, and after a few moments in the layers you will see that we have a wildfire data. First, go to the layer setting to make a color composite for the day number 8, a combination of near infrared and red. Using the 3 bands, you will be able to make a multi-comp, you will be able to composite multi-bands together to make a false or true color composites. So we have 3 channels here: the red channel, green channel, and the blue channel. These are the main color palettes. So if I set the band number 2 for day 8 to the red, and also the band number 1 or the red region to the green and blue portion of electromagnetic spectrum, I will have a false color composite in which vegetation cover showing with the red color. Through the stretching technique, I will be able to improve the quality of visualization, and after a new range of value applied, click on apply and check the VIIRS wildfire on, and after a few moments you will see that this is the image for the October 8, the day number 8, and also nothing can be seen in this image. So we can try for the next one. The next one, the day after starting wildfire, is the day number 9. Now I'm making another false color for one day after. I'm setting near infrared to the red and also the red region to the green and also the blue channel. Again, through the stretching technique, I'm increasing the visualization and click on apply. After a few moments, you can see the burning area. Now it is clear, and now you can see the regions that are under fire clearly, because smoking are releasing to the air, and also this their pattern showing that some region near to Sacramento or northern California are under the wildfire. You can see the smoke pattern releasing because of burning condition in the forest and vegetation cover. You can see that easily you can find the locations that are under the wildfire in this big region. You can see the regions that are under fire. So you can select one of them for the further analysis with higher resolution data. You can select this region or this one, no difference. Just I want to pick up one of them and then do the wildfire detection and its impact analysis on the vegetation cover. So to select one of these regions, make a new geometry. So as you can see, make a new geometry through drawing a rectangle. I am drawing a rectangle that covers the burning area completely. I'm trying to cover this region completely, as you can see here. In the next step, we need to have focus on the new region that we know that was under wildfire situation in the October 2017, because we found the location earlier, and now thanks to Landsat images we can compare the situation before, 1 year before and 1 year after the burning in this region, to see that how vegetation cover changed comparing before and after situation. So through the map.center object, I want to have focus to the geometry number 2, the green border selected. Make a new layer make a new image for before equals to, so now for 1 year earlier in 2016, the Landsat 8 and Sentinel-2 images, both of them are available, but I'm gonna use Landsat data for this tutorial. Through the search places and dataset, just type Landsat 8 collection 2 level 2. The reason behind collection 2 and level 2 data is that they are surface reflectance values and already corrected radiometrically and atmospherically, and these are the best options for the spectral indices analysis. Import it into the code and then assign it to the before variable. Make a new image collection for the before, but the second image collection including Landsat 8 data. As you remember, the first collection was related to the VIIRS data. So make a new filter date. The filter date I'm gonna work based on is related to the October 2016, the same month but 1 year earlier, before the wildfire in 2017 occurred. The filter date is for 2016, and the end date could be 2017. Instead of this format that I have used before, you can also use the filter date. You can use the calendar range. This is another kind of temporal filter and helping you to set different temporal filters to your data. Weekly filters, monthly filters, annual filters. It is also very useful. And if you followed my tutorials in my YouTube channel, definitely you saw that I've used a lot this function in my tutorials. Earth engine.filter.temporal collection. Filter.calendar range. It was my fault. The calendar range including 3 arguments. The first is the start, the end is an end date, and the field should be here based on the month. I need to call all Landsat images in 2016 belonging to the October, the month number 10. So the start and end month could be number 10, meaning that I need to call all the Landsat data only for the October 2016. But don't forget to use .filter bound. We didn't use the filter bound for the VIIRS data because it is a coarse spatial resolution data without framing structure, and also in that case no need to use the filter bounds. But for those of satellite data such as Landsat with mid spatial resolution and framing structure and having a specific pass and row for each frame, it is necessary to use the .filter bound to bounding and limiting your data to the region of the interest you are working. The region of interest here is the location of the wildfire, the geometry number 2. So then I need to select the target bands. The target bands go to the data description in the Landsat page, and then you can get information about the Landsat bands, data descriptions, and data characteristics. As you can see, there is a scale and factor for the surface reflectance bands. So then I need to get a scale, I need to get a scale and offset first, and then apply it on all surface reflectance bands, because I need to do visualization in the first step, and then I need to calculate the NDVI index to compare the vegetation changes after and before the wildfire, date. Back to the code. But in the first step, we need to do just a visualization with the false color images and comparing what was before and what is now after the wildfire. Map.add layer. So I need to see a median average from the region of interest that is clipped based on the geometry number 2, and then for the visualization I need a combination of the false coloring data, a combination of near infrared, red, and green band to make a false color composite to show the vegetation cover clearer. So the combination of surface reflectance band number 5, surface reflectance band number 4, this is the red region, and surface reflectance band number 3, this is the green region of electromagnetic spectrum. Layer name is before RGB and use the false. You can use the same code for the after situation. Just copy and paste the previous code with the small changes. The variable name turn to after, same image collection. Using .select, we can select those of the bands starting with SR, and the rest of the words and the rest of the letters not matter. SR like this. So the next is about the filter date. We need to compare the the region in the same month 1 year before and 1 year after the wildfire occurred, after the date in which the wildfire occurred. That's why the starting date for the after could be 2018. So, and now in the visualization, just we need to change the name of input variables and keep the same band combination and just change the name of layer. This is the after RGB. Save your code now and run it again. When you run the code, this time you will have focus on the study area on the second region you have selected before. Remove the layer 1, have a more focus on a study area, and remove the geometry number 2, and first visualize the before condition. As you can see, this is before false color composite 1 year earlier from the wildfire occurred in this region. This is the cloud shadow that you can see its impact in the data. So, and here in the after RGB, you can see that how vegetation cover changes 1 year after. As you can see, the red regions showing the vegetation cover and the dark regions or black regions showing the burned area. Seems there are also other places that should be considered in our study area. It's very simple. You can call the geometry again and select a bigger area, and also you can reduce size of the regions by remove some places that's not affected. This helps you to define your region of interest more accurate. Run the code again, and here now you can visualize it better. So the before image have a more focus. This is a before situation or before condition with 98% stretching technique. Here you can see these are the cloud shadow in the region. After getting median image, you can see its impact is its impact are clearly shown in the data. So, and now the after wildfire, you can see how vegetation cover changed. Hopefully this is a cloud-free image and showed that how much vegetation cover changes after the wildfire occurred in this region. To remove the cloud shadow impact on the final in the previous data or before RGB, because it is very important to compare the data in a cloud-free situation, because when you want to do the change detection, it is very important to have access to cloud-free images, because definitely the shadows region, the regions that were under shadow, definitely will have negative impact in the final change detection results. That's why we need to reduce the impacts of cloud. To increase the number of available images, I can set a longer period of time for the before image and also the after one. For example, I can set 2 or 3 months for the median value that helping us to have more images and have a more accurate median estimation. For example, here I'm setting a starting to the number 8 from August to October, and then from August to October for the after and before. Run the code again. The code is running. The before RGB is producing, uploading actually. This is the before image. Hopefully now it is completely cloud-free, and we have no problem regarding to the cloud and shadow. And also for the after RGB, again we have a same image, cloud-free image for the same period of time, and I'm increasing its contrast by 98% range of values, and now that's what it looks like. You can compare the situation after and before the wildfire that occurred in this region. Even you can increase the region of interest a little toward the east, but it totally depends on you how to define your region of interest. So this is a kind of tutorial, just I'm sharing the techniques with you and then it is up to you how to define your region of interest with which border. So for the next step, I need to calculate the NDVI for the after and before situation, and then do the change detection using subtraction technique in the next step. Because the wildfire mostly changed the vegetation cover in the region of interest, and that's why I'm gonna use a vegetation index to assess how much vegetation cover changed from one time to another time. So let's go to the code. And also there are some codes and algorithm for the actually burned area detection. I'm gonna also show you how such kind of algorithm will work. So now I need to calculate the NDVI for the before and after variable. Make a new variable as NDVI before equals to get images that are in the before variable, then making a loop and calculate the NDVI for all images included in the before variable. To do the calculation, make a function that each input image considered as an IMG, and now in the function body, you can write the rest of your code. So for the first step, from each input Landsat image, I need to extract the gain and offset coefficients for the conversion from digital number to the surface reflectance values. As you can see, in the band names mentioned that there is a scale and offset for each band that is same. For example, the scale value for all the bands is same and the offset value for all the band is the same. We can copy and paste this value into the code, or even we can extract these values from the image properties. As you can see in the image properties, that is a kind of metadata, there are various information that helping us to extract the target coefficients. For example, as you can see here, there are different information, but I'm looking for the coefficient, but they not mentioned here, but I can show you in the code editor environment. So to get a better understanding about the property informations, I'm printing one of the Landsat data. For example, one of the before images printed, the first one selected, and now just I'm gonna show you what the properties we have in one of the Landsat data. This is the Landsat data that you can see various type of information is available here, and even more than information mentioned in the data description. As you can see, the coefficients for the reflectance bands, the gain multiplication value, and the value that will be added to each band as an offset is listed here. So from each input image, just I can extract one of the coefficients for the add and one of them for the mult and apply them on all the bands and then calculate the NDVI. To do this, I'm making a gain first from each input image. When you want to get something from properties, you need to use .get. When you want to select a band, you need to use select. But for the working with properties, you need to use .get. So the reflectance add band .get, I'm gonna get in the reflectance add band, need to convert it from a string to the number using VIIRS engine.number, and then another value is the offset. Make a number function from each input image get the reflectance, for the gain we need to get the value that will be multiplied to the input image, and the offset is the value that will be added to the main image in a simple linear equation. So here you can see it better now. Yes, the gain and offset extracted. The gain and offset here are the values in the bands that you can see as a scale and offset. They are the same. So just I'm extracting from the properties. So make another variable as a surface reflectance bands SR equals to from each input image get the main image or the main band and multiply it to the gain value and add it to the offset value. So this is a simple linear equation that allowing us to do the conversion from the digital number to the surface reflectance range of values. So after SR calculated, make another variable for NDVI, Normalized Difference Vegetation Index. So NDVI equals from input surface reflectance data that's normalized difference. Calculate the normalization relationship between near infrared SR band 5 and SR band 4 B4, near infrared and red, and rename it as NDVI B4, just like that. The function returning the NDVI as the final result. So, as the NDVI calculated for a period of time from August to October in 2016, we need to make a single NDVI value that must be clot-free image. So that's median, helping us to get an average for that period of time. But the question is, why we are using the median instead of the mean value? Actually, the median reduces the impact of extreme values that may occur because of the internal noises or cloud impact. So this is the NDVI before. I can copy and paste it for the NDVI after with the little changes. NDVI after equals to get after images into the same function with the same gain and offset values and the same equation and also the same formula for the NDVI calculations. So the NDVI after the median average is also calculated. And now using the map.add layer, we can visualize and compare the NDVI values before and after wildfire. Map.add layer, first NDVI before, then clip it based on the geometry number 2, leave the visualization parameters empty, and the layer name is NDVI before first, and use the false. As you know, false helping us to avoid automatic visualization that could highly reduces speed of processing. Use the same add layer, this time for the after NDVI. NDVI after, just like that. Instead of NDVI before, we have NDVI after. Save your code and run it again. So, code is running. After a moment, NDVI before is available. This is the first NDVI value for 2016 1 year earlier or 1 year before the wildfire events. Increase the contrast by 98% stretching technique to improve the contrast. And then we have the NDVI after. You can see the differences between NDVI values. Use the 98% enhancement. Now using transparency, you can see that which areas affected after the wildfire. So you can also see the changes in the histogram for the first and second NDVI. As you can see here, we can visualize the changes in the histogram using histogram plots. So user interface .chart .image .histogram. The first input NDVI before, the second region of interest, and the third is the spatial resolution 30 meter. And then we need a title for the new histogram. The title could be equals to NDVI before 2016, and then we will have the same histogram, but this time for NDVI after. NDVI before and NDVI after. Same region, same spatial resolution, but the different name and different year. 1 year after the wildfire occurred. So now in the right panel, you can compare the histograms before and after wildfire. So because of size of regions, too much pixels included. So we need to reduce the pixel size to 100 meter to solve the issue. Code is running again. Two charts are under generating. So as you can see that this is the NDVI before and this is the NDVI after. As you can see here, we had actually single mode histogram before the wildfire happening, but after that you can see we have a multimodal histogram pattern. As you can see that vegetation cover decreased, and as you can see in the vertical axis, the frequency of higher NDVI values clearly decreased from 3000 to 20,000 pixels, and the density of low NDVI values close to the zero increased. As you can see here, we have a new mode that we didn't have before. This is occurred because of the wildfire, because most of actually vegetation pixels removed and turned to the zero, and also you can see that you will see the impact of new pixel values in the new histogram with higher, lower NDVI values in the second image. This histogram also confirming the reduction in the NDVI values after the wildfire. You can see the changes visually and statistically. In the next step, I'm gonna show you how to highlight the regions affected from the wildfire with more accuracy in a single image instead of comparing two histograms or comparing two images for different dates. let me to make a bigger space for the rest of code first. So it is a very simple technique. Using subtraction, you can get a subtraction between NDVI before and NDVI after to visualize the differences between the before and after image. So make a new image as NDVI change. This is a new, actually this is a new variable. NDVI change equals to, so NDVI before dot subtracts. The subtraction is one of the simplest and the most popular technique for the change detection between two single images. Dot subtract from NDVI after, just like that, and then through the map.add layer we can visualize it. Map.add layer here, the NDVI change, leave the visualization empty, but before visualization you need to clip it based on the second region of interest, and the layer name is NDVI change, and use the false at the end. Save your code and then run the code. After a few moments, you will have a new result as NDVI change that's highlighting the changed area after the wildfire. You can increase the contrast by 98% stretching technique, and here the region affected from the wildfire, or the regions in which the vegetation cover destroyed, actually completely highlighted using the NDVI change detection. But there is a problem here, the water area. As a water is a dynamic phenomena and its reflectance value actually changing during the time, you can see that the NDVI value also changes over the water from the one time to another time. That's why you can also see some negative impact of water in your region of interest. For example, in the NDVI before and after, you can see that the main area that was under change was related to the wildfire, but the lake didn't change a lot. You can see that nothing changed in the lake, but we have some small reflectance changes over the water. And now we can remove the water bodies from the input images or from the output to improve the accuracy of estimations. Yeah. In the next step, I'm gonna show you how to remove the water from the output images. So, the simplest way is using the land cover images. For example, as you can see, the dynamic world land cover data with 10 meter spatial resolution is available. Just type the dynamic world land cover. As you can see, the dynamic world version 1 is available. Import it into the code, and now I can make a median image from the land cover, or from we can make a mode image from the land cover data from 2016 to 2018 for the period of time we are working. So I'm gonna make a water mask first, equals to the input image is collection number 3, the dynamic world product, and then I'm selecting the bands including the different classes. If you go to the data description, you will see that here in the bands, as you can see in the bands, there is a band as label that's including all the classes and also ranges from 0 to the 8. And the water is class number 0. So we can highlight and select the water area with number 0. It is our threshold. So now First, I'm gonna select the target band. The target band is a label. As it is a multi-temporal land cover data, I need to get the most frequent classes in each pixel through the mode. This is another statistical operator we are using. That is very popular mode for the getting mode for the land cover data during a period of time. So as the water pixels including zero value, I'm gonna highlight the pixels that including value with number 0. So then to see the mask visually, use the map.add layer for the water mask this time. Leave the visualization empty and clip the mask based on the geometry we are working. And then use set the name as a water mask and use the false at the end. Run the code again. The code is also running. Save your code and zoom to the value, zoom to the region. Click on water mask to see the mask created for the water bodies in the region of interest. It's a little taking time for the visualization. Now it is loading because large number of data we have in the actually land cover dynamic world product. Too much images involved in the calculations to select the region and also show the result. As you can see, all the water bodies highlighted here, but I'm waiting to be loaded for the rest of the region. So you can see that the water bodies showing with the white color or value number 1. But we need to have the value number 1 for the non-water pixels and 0 value for the water pixels. That's why I need to use .NOT at the end, because this is supposed to be a water mask. The water mask is a kind of image, is a binary image with 2 values, 0 and 1. 0 for the water and also 1 for the other pixels. I'm still waiting to see the final result for the rest of the area. To be sure about that it is completely covering the water bodies in my region of interest. Yes, now you can see it is completely covering the water bodies, and now I can apply this. I can apply this water mask on the data. But as I added the not at the end, the binary image will be changed. The value 0 for the water bodies, the value number 1 for the non-water pixels. So here we will have NDVI change that is masked equals to NDVI change dot update mask based on the water mask. So finally you can see the updated change map. This is NDVI change mask clipped. It is masked, and run the code again to see the final result. The NDVI changed mask is under calculating, definitely taking a little bit more to show the final result because it is involved in more process because of masking and so on. The image are uploading, and also you can download the final data, the masked NDVI value using the export.image to drive, and I will show you how to do this in the next step. As you can see here, now the final data is created, and also we don't have any impact of water in the final results now, and now we can have better estimations about the situation of the NDVI changes for the further analysis. Even you can calculate the areas in which vegetation cover changed. I'm gonna increase the contrast by 90% stretching technique to get a better visualization. After the range of values updated, click on apply to see the final result. Just like that. This is the change map that is created. In the next step, we can also set a threshold to make a binary layer to separate the changed area from the non-changed area. But before then, I'm gonna show you how to get export from NDVI changed mask in case you want to have this raster layer in the desktop software. Just use export.image to drive. The input argument is the input image, that is NDVI change masked, and remember to clip it based on the region of the interest, and the description is the name of the output, Wildfire change, and use the scale as a spatial resolution for the output image that should be here 30 meter, or if you faced with any problem for the export or something like that because of the region extent or too much pixels in the region of interest, you can reduce it to 100 meter. It is totally up to you which kind of a spatial resolution you want to use, but originally it should be 30, but to avoid some possible errors, you can reduce it to 100, and then maximum pixels equals to 1E13. The region of interest, it could be geometry number 2, and the CRS, the coordinate system for the output, equals to EPSG 4326. Save your code and run it again. In the right panel, you will see that in the task, after a few moments, a new image is available to be saved in the Google Drive. Just click on run, and now as you can see, if everything is okay, click on run and wait until the color of actually this tab turn to the blue, same as the previous code, meaning that the process of saving is completed in the Google Drive. So this is how actually the wildfire detection works. In the next step, I'm going to show you how to set a filter to make a binary image for this region, and then how to calculate the area. So for example here, first I'm going to make a histogram through the user interface chart image histogram. I'm gonna make a histogram for the NDVI change that is masked. Here, copy and paste it as an input. The region is geometry number 2, and the spatial resolution should be 100 meter. In the right panel, under Console tab, the third chart that is under Generating will show the histogram for the changed NDVI map. It is under Generating. We are waiting to see the new histogram values because the new histogram is going to help us to find a threshold to separate the burned area from the other region. Another way is upload the NDVI changed and use the inspector to get understanding about the values in the changed area. For example, the console, still we are waiting to see the results. Until then, I will show you how to use the inspector to get understanding about the changed area range of values. Once the range of values updated, click on Apply to see the final result. Yes, there is. And now go to the inspector and click on each pixel. Too much images here we have, and also it's maybe a little difficult to understand what's going on, but the main image is NDVI. The main image is NDVI changed mask. The band name is NDVI before, that is wrong, that we can change it through the .rename. Here just I can make a rename to turn it to NDVI change. But anyway, the value is positive definitely, and also it is greater than 0. But the actually burned area, you can see that they have a negative value. They have the negative values, and meaning that the positive values or values greater than 0 could be a good threshold to differentiate the burned area from the normal regions. The chart is still under Generating. That maybe takes a little bit more, but until then we can get a better understanding about the range of values if histogram doesn't work like here. So again, you can see that the values greater than 0.1 could be a good threshold to separate the NDVI changed mask here. So the NDVI changed mask dot clip it based on the geometry, and now I can use the threshold, but still I'm waiting for the chart generating. You can run the code again, but if a still problem exists and also you can't see the histogram, you can set value 0.1 as a main threshold to separate the burned area from the normal region. Yes, it is still under Generating, but it is okay. I'm making a threshold value equals to from NDVI changed mask. So here I'm making a threshold. The input image is NDVI changed mask. The pixels greater than 0.1 should be selected, and this is a binary image in which the burned area will have value 1 and the normal pixels will have 0 value. Through the map.add layer, you can see the final results, but it is a little time consuming. Just I skip it and go for the further analysis. Then we need to mask the non-burned area as a no data value. Just here, get the threshold and use the update mask to remove the 0 values from the input image. Then, using the map.add layer, we can visualize the mask that is clipped based on the geometry number 2 without any visualization settings, and the name is the mask layer, and use the false. Run the code, and after a few moments you can see the burned area as a single layer without any background. So click on mask. I'm waiting to see the final mask, and also the final histogram is still under generating, as it is very time consuming process and maybe will have negative impact on my code, I prefer to remove it from the code, because the actually the masking process on the final data will have a negative impact on the speed of processing. So here, that's why I prefer to remove it. And now you can see the burned area with the threshold I have set. The histogram here turned to the text because it reduces the speed of processing for the next step. So in the next part, I can calculate the area of each selected pixel in the white region. And definitely we will have some noises in the final result that could have negative impact on our estimations. So you can change their impact or reduce their impact by setting a larger value for the threshold, such as 0.15 or 0.2, because it's also helping you to reduce their impact in the final estimations. So get the mask image, then multiply VIIRS engine.image.pixel area. I need to calculate the area of each pixel for the burned region. So if you want to convert it to the square kilometer from the square meter, divide it to 1 million. So in the next step, after the area of each pixel for the burned region calculated, I need to get some of the areas. So the final area equals to from area image dot reduce region. The reducer is VIIRS engine dot reducer dot sum, because I need the sum of the values, and geometry is geometry number 2, and scale here should be 100 meter, because we have a large extent and it will have impact on the speed of processing. And also as you saw before, maybe we will have some issues regarding to the pixel densities and spatial resolution in this region. Run the code now, and in the right panel under console tab you will see the area of burned region. Oh, I need to print it. Sorry. Print the final area. Here you can see that it is calculating under a dictionary. If you want to convert it from dictionary to a value, it's also very simple to use VIIRS engine.number first, and then use .get the first value and .values before. That's helping you to get the value for the final area. We have a large extent, and also now you can see it is converted to a number, but it's a little time consuming because we did a lot of processing until now, and also the area of region of study is a little big, and that's why it's taking a little more time to do the calculation. If you want to increase the speed of processing, the best option is reducing the pixel size here or the scale value here. Just need to wait and also run the code until to get the final area for the region of interest. And remember to save your code to keep everything in your code. And also one more thing is that if you faced with any problem, and if you had any issues regarding to the code, my code link is available below the video description on my YouTube channel. You can reach me out there and also find the code link. It is available in my GitHub. and you can compare yours with mine, and if the problem still exists, you can reach me out in the comments and also put your comments asking your question. I will try to help you to figure it out what's the problem in the codes you are working. But after doing comparison between mine and yours code and your code, definitely you will find a solution. And also I hope you like this tutorial, and just I'm waiting to see the final value. That is a little time consuming. Until then we can go to the task, and you can see that the wildfire change image is created, and we can download it from the Google Drive. Go to the Google Drive in the data description here. It is still under computing. I can also remove the histograms to increase the speed of processing. Yes, I hope it works and helps to see the final results. And the another solution is reduce the pixel size to 250 meter. I hope it works. Go to the Google Drive to see that yes, Wildfire change image is also available. By right click you can download it to your own system for the further analysis. But the speed of processing in my browser reduced a lot, and that's why I cannot do the actually downloading process immediately. Sorry for the problem. But if you click, or if you right click on the Wildfire change, you can download it easily into your system, and still the number is under calculating. In that case, try to save your codes, because maybe you will face with some errors in the calculations, and also not responding problem that's caused quitting from the browser. But before that, make sure to save your code. It's still not working. I'm trying to reload it. Seems my region of interest is very big. I'm trying to reduce it to 1000 meter, just trying to show you how the result calculated. That's it. I'm going to the Google Drive. Still not working. Yes, the final area that is calculated after reducing the pixel size or scale value is 1830 square kilometer. The estimation for the burned area based on the NDVI index. You can also use some other indices such as normalized difference burn ratio and something like that I will teach you in the next tutorials on my YouTube channel. But you can see that using the NDVI you can assess and measure how the vegetation cover destroyed after the wildfire. And also here the wildfire change is also available, but unfortunately my browser not working now. But using the right click and clicking on download image, you can download it and open it up in the desktop softwares you are working. I hope you like this tutorial as much as I did. If you had any question or problem, just reach me out on my YouTube channel, and thank you for your attention.